Hello everyone. So on day 17 of 75 hard research challenge, I studied the question that whether we can use large language models to do planning. So I'm going to give a brief introduction on that. Let's get started. So before we jump into whether LLMs can be used to do planning, let's first see what exactly is a planning task. Okay. So let's say you're given a floor and you are given three boxes with you, C, A and B. Okay. So this is the initial state of these boxes and your goal state is to stack these boxes in this particular order. That means the should be at the bottom, B should be above C and at top it should be A. So this is what a typical planning problem would look like. And how do you solve such a problem? By taking a set of actions. You are given a set of actions and based on a particular action you will move to the next state. That means that in this case you are given a state ST, you take an action AT and you move to the state ST plus 1, right? This is similar to what you might have seen in the case of reinforcement learning. The difference between planning and reinforcement learning fundamentally is that you are also given with you the domain model. That means you are given the transition model. That means what will happen if you take a particular action. For example, you will be given a function, the probability of ST plus 1 given ST and you take T, right? You take AT action. So this probability distribution is missing in the case of reinforcement learning, but is provided to you in the case of planning. Okay. So now let's see how to solve this problem or how a classical planner can solve or build a plan out of this particular problem statement. So the first solution would be to put this box A on the ground, and that's when you take that particular action you get this particular state, right? Next action could be to pick up the box B and put it on the top of box C. So if you take that action, you reach in this particular state. Now once you have taken this action, let's say you are left with taking the action that pick up this particular box A and put it on top of B. So you will be left with the particular this particular state, which is our goal state, right? So this particular sequence of actions of putting A down, then putting B on top of C and then putting A on top of B is a valid plan. Okay, so this is by definition what is called a valid plan. So let's see what LLMs can do and cannot do. Okay, so long story short, LLMs cannot plan in an autonomous mode. Okay, so they need some form of human in the loop kind of a thing going on with them, right? They also cannot improve to a very large extent by using self verification, or also known as self critique, where you ask the LLM a plan and then you ask the LLM whether the response plan is valid or not and whether it would like to correct that plan or not. So you continue doing this cycle up to k steps, and whatever final plan you get, you say that this is the final output of the LLM. But the problem with that is that LLMs do not know how to do planning in the first place, so they do not know how to self-critique themselves also, right? Third, which has been noted by a lot of people in lot of areas of using large language models, is that LLMs are very apologetic in their outputs, right? They cannot plan without a human in the loop. Okay, so most often than not, this particular image is very famous, that impressive abilities of large language models in this case, and there's a huge system that is built on top of it, very fine grained, and but all of this is balanced on a single pillar, very small pillar, that is the prompter already knows what the answer is going to be and what the answer should be. So indirectly or directly, we often give the prompt which facilitates the LLM to generate the output. This itself is known as prompt engineering. This is a whole area in itself, right? So if we cannot use large language models for this, what can we use them for? Okay, so they can be used as a helper things. For example, they can be used as external, they can be used to guess a particular plan. For example, they can, let's say you have an LLM with you, you ask the LLM, okay, this is the query with me. You give it to LLM, the LLM will give you a response plan, right? Let's say P1. Then human will evaluate it, or there will be a symbolic module that will execute this plan and say whether you achieved the goal state or not. Based on the response, you will give the response back to the LLM. The LLM will now edit its response based on the output and refine. This refining process can continue to happen, right? Second, it can be used to explain a particular problem statement. For example, in this particular domain, we have blocks with us and all. So all these explanations can be like generated using large language model. Okay, so this can be helpful for multimodal settings, right, where you have a sentence as well as a symbolic state as well as a image of the environment going on, and that can eventually align with each other to provide a better policy or better convergence towards the policy. Okay. Third is that it can translate from one problem like form a description language to another. For example, traditionally what people use is called something called PDDL, and there is a newer version of that called RDDL. Right? These two are just simply description languages which are used to define a particular problem statement for a planner to take as input. Right? These are simply files. Right? For example, you have a TXT file where you write text. For example, you have a C file which has the C code. Similarly, you can define a problem statement in planning using PDDL or RDDL. Let me know if you need a detail on this. I can create another video on that. Okay, so now this was a paper I was reading, and some of the slides and some of the summary of this particular video comes from a talk by Subarao Kambapati. I would recommend and leave the video link. You can watch it later. So they performed a set of problems where you have this blocks world that we saw earlier, and we see that GPT-4 performs very good, that it solved 34.3% of the problems out of 600. That means it can solve roughly 1/3 of the problems, right? And similarly, they tried GPT 3.5, which is famously known as ChatGPT and other versions of GPT-3, and they were very low on the performance, right? Now they tried another domain and they saw that it can perform 14% of the time, while the vanilla earlier version of the GPT, that is 3.5, can perform only 0.5% of the time. So that led them to question that are the LLMs actually able to grasp the planning problem, or are they just leveraging some form of information that they might have seen during their web crawl data that they have been trained on, right? So they did another experiment in which, rather than using general terms like blocks and floor and having names for actions like put or pull or keep down or push, they obscured these words by something else. For example, they can say for push, they can say for push they can randomly choose some string, for example ABCD, right? So you have an action of with name ABCD, then you for pull you may have an action of name XYZ and all, right? So XYZ has no particular meaning in the English language for that can relate it to push or pull, right? Type of action for, and right. So all these things they tried, and if LLMs could actually solve a problem, then what would happen is that they can get the same level of accuracy. But surprise, surprise, what happens is that accuracy, that means they asked deceptive words, right? Or they use random words for actions and states or to define the domain. The accuracy drops extremely low, right? From 34.3% to 4.3% and then to 2%, right? If you use randomized word. So that essentially says that large language models, the embeddings that has been created of various tokens and all are extremely helpful in the case of planning, and can give an illusion that you are actually planning, which in this case we see that they are not actually planning. Okay, so what we can do now, what do we do with this particular type of information is that we can do some form of fine tuning. Right. What we can do is that for each domain like blocks word, you can generate n number of or practically infinite number of plans which are valid using some form of classical planner, right? And then you simply used supervised fine tuning to fine tune or like a large language model. But then again, this will be extremely costly, and it is not very clear why would you want to do that. Maybe if you want to create a single LLM that can solve 20 domains and all, maybe it's a good experiment to do, but it's extremely costly, right? In general, it has been seen that LLMs are very good at style critique rather than correctness critique, right? There is a difference between these two. For example, in the case of plan, planning, you need a valid plan that can be executed. For example, in this case, if you give an output as a function, as an action, that okay, put b on top of b, so that's not a valid action, right? So LLMs can end up doing that because they hallucinate and they are not well grounded in the reality, right? Maybe we can use some form of RAG system here, I'm not sure. Okay, just throwing out an idea, thinking out loud. Okay, so people say that LLMs are good because in the cases where they are able to judge a good distribution, and there is no very clear cut objective metric to judge the quality of a paragraph. If you ask the LLM to write a story on unicorns, right? So it's very difficult to judge or to categorize the quality. If it is good enough, it is good enough, right? We may be able to criticize them saying that this is bad, this is good, but to some extent only, right? But for planning and all, you need correctness critique. So if you can do that, if the LLM can do it, then we can use self critique and all that stuff. So there are some benchmarks that people have created around it. For example, travel planning benchmark is there, plan benchmark is there, right? Then why is it that people think that LLMs can reason and plan? So one of the reasons is that people often mistake acting with planning. Planning would require you to pick a particular action and then execute it. Acting would mean that you are simply picking some random action, right? For example, if you have it's like a child in a room. And this is a very good example given by Professor Subbarao, right? He said that if you have a gun in your room and a child goes in the room and picks up the gun and shoots, then that's acting, that's not planning, right? So you would not want that. So that is what LLMs are currently doing, that they are some form of good actors, and that is what people are getting hyped on. Okay, but then the question is, how do systems like Copilot work? Because Copilot is writing code for you, right? So it is organizing the code in a particular sequence. It has to decide whether it wants to use a particular int or float or so on and so forth, right? So it is planning in some form, but there's a catch in that people, the data set that is being used by such Copilot systems to be trained on, supervised trained on, is highly like positive and highly of high quality, right? Because people usually do not put their bad non-working code on GitHub. Okay, so and there is always a human in the loop that is going to correct the code once it has been written. You simply do not pick the Copilot code and deploy it on your server, right? Now the question is that how would we use LLMs in planning? So you can think of LLMs as approximate knowledge sources, right? So you can think of LLMs, for example, we saw in our experiment in the table that if you use normal words like pull, push, block, floor, then it gives a very good performance, right? So that means it has a very good knowledge of what goes on when you say pull or push it. The word embeddings or token embeddings for pull and push are very good. So they can be used to have that wide sense of what goes on in the universe, what goes on in the world in general, in relation to humans and other things, right? And then you can use you can combine it with some form of non-expert expert user which can interact with the LLM and refine it and so on and so forth, right? Second, we can also use it to use as a heuristic planner, because the plans of LLMs are not that good. Maybe you can use it to create heuristic functions which can then be used to plan by, or maybe used by symbolic planners or classical planners. Okay, we can also use LLMs to write various domain models. Let's say you can there has been work where you by Google, I think, where you give us a description of a domain or an environment or a video game, and it will generate the video game in the form of like traditional video games, right? So maybe you can use LLMs for that and then make a planner on top of it. Further, you can use LLMs for human preference modeling. For example, safety is a big concern in robotics, etc., right? So maybe if a robot generates a plan, it can ask an LLM whether the plan is going to hurt a human or not. So that type of human preferences or safety mechanisms can be added using large language models. Okay, so that's all for today. Thanks a lot.